rules for deciding. Just like our rule here, it's a convention, but it's a useful rule. If you get 7 successes in a row, something is funny. Okay. I want to switch topics to what is called a bell curve or a normal curve. And there are all these graphs of normal curve. And you should ask the question, why is normal curve important? I will answer that. But a normal curve, it has on the x-axis the values and on the y-axis the frequencies of people. Okay. And there are 2 parameters which are important: central tendency, the mean, and the variance. So this blue fellow has very low variance. So it's a thin curve, it's a tall curve, and its mean, the center is at 0. Whereas this brown fellow, its center is also at 0, but it's very spread out. So it's a very fat curve and short one. What about this green fellow? The green fellow has a mean which is -2. So the mean is different. What about its variability? Its variability is more than this blue fellow, but less than this brown fellow. Okay. And this red one, its mean is 0, and its variability is more than the variability of the blue and less than the variability of the brown. So when variability is high, the curve becomes flat and spread out. Variability is low, curve becomes thin and tall. So if variance is low, values are closer to each other. If variance is 0, all values are identical. Okay. So as variance increases, values spread out a lot. So this is generally the pattern in the data. Why are we discussing the normal curve, the bell curve? Why is it so commonly used? In biology, there is a reason. Polygenic traits like height and weight are bell-shaped because what you see, the phenotype, the observable, is a result of effect of many genes added together. Okay, and there is a theorem in mathematics: if there are tiny influences and they are all added, then the final result tends to become bell-shaped. And look at this picture. This is an interesting way of showing that human height is normally distributed. On x-axis, you have height in inches. So look at this. This is 66 inches, 5'6", 5'7", 5'5", and that is where all the people in one row have the same height. So 5'5", 5'6", 5'7", you have maximum number of people. Whereas this girl is 73 inches, that is 6'1", only one person. 6 foot, this one is 6 foot, only one person. This is 1 inch less than 6 foot, 3 people. Similarly here, only 5 feet, 2 people. So the point is that female height, and this is North American, white people, so the average is around 5'6", and the number of people around the average, many, and number of people far away from the average, either on higher side or lower side, is very small. That is how the normal curve generally is. Okay, so that is why for all typical polygenic traits, you get normal curve. And that is why statisticians use normal curve all the time. A tool called odds, and this word is used in common English also. Odds in favor, odds against. The fellows who go to racetrack will talk a lot about odds. Okay, so we will now tell you the definition of odds and what to do with it and odds ratio. So we are comparing only two. This is used for comparing two groups, poor and low income. And we are talking about data on stroke. Why? Oh, there are plenty of variables there. You could do it for any. This is just an example. Now stroke for poor. Now look at these counts. There were 638 poor in that study, and 46 had experienced a stroke, and 592 did not. So how do you calculate odds? Yes, divided by no. 46 people did have stroke, 592 people did not have. The ratio is 0.08. That's for odds. odds in favor of getting stroke. Okay. Similarly, for low income, it will be 69 divided by 963 and it is 0.07. So here odds are 0.08, here odds are 0.07, and then you take ratio of those. That's called odds ratio. Okay. And this is 1 point something. Now, what is the interpretation? If odds ratio is 1, it means for both groups, the risk is similar. If odds ratio is away from 1, then the risk is not the same for two groups. Well, this is also away 1.14. How do you decide whether it is away? P-value. Okay. Everywhere we will be looking at P-value. So, is the odds ratio close to 1? Is the difference from 1 just due to chance? Or is it a systematic difference? If the odds ratio is close to 1, then the risk of stroke for poor and low income is similar. Now we find the confidence interval. How do you find it? That's mathematically a bit complicated. Software will give it to you. In this case, it is 0.74 to 1.6. So the true odds ratio is somewhere between 0.74 and 1.6. So 1 is a plausible value. Okay. So when you get that kind of a confidence interval, you say, the risk ratio is not far away from 1. Z statistic here is 0.41, p-value is 0.68. So the two groups having similar risk of stroke cannot be rejected. Again, I am looking at p-value to judge. And all these numbers should be given to you by software. And whatever software that you will use, you will have to spend some time to learn how to extract these from the output. So the hypothesis in this case, namely that poor and low income group have similar risk of stroke, this is okay.
Nutraceuticals trials, and we are doing a lot of original research. So
there 0.05 may not be a good value. 0.1 may be a better value.
Okay.
See, if you have 10 treatments, the most important thing is get rid of the useless fellows. In a clinical trial, the most important thing is not success, but quick failure. Because if you don't recognize the useless fellows, they keep tagging along and the expense goes up. And in the end, they create, So at early stages, when the number of treatments is very large, it is much more important to drop the useless ones than select the successful ones. It is the age of the bird, and on the y-axis, it is the weight of the bird. So what is poultry business? They acquire one-day-old chicks from suppliers, and there is a lot of technicality here. And then they feed the birds, and they hope that the birds will quickly grow, and then they will be able to sell the fully grown bird at a profit. So the phenomenon is increase of weight with age. Okay, and correlation can be very high. So very strong correlation. Now we want the equation. We want to be able to tell at what age what will be the expected weight of the chick. And in this case, the weight at a particular week is minus 95.4 plus 237 into the week number. And how do we use this equation? Well, we can input the week number 1, 2, 3, 4, 5, 6, and we will get the expected weight at any. So now, instead of any other number, I put 10 weeks. What do I get? So 10 weeks gives me 2370 minus 95, so it is about 2274 grams. That is about 2 kilos and a quarter. That's a big bird. Okay. But what if I kept feeding the bird much longer, for 100 weeks, 2 years? Then this equation says that bird will be 23 kilogram in weight. Is that possible? Has anybody seen a poultry bird who is 23 kilograms in weight? Absolutely not. Absolutely not. So this is the first thing to remember in using regression, that because there is an equation in your hand, you have the freedom to substitute any value of x, But if you don't take care, what you get will be useless. Going beyond your data is called extrapolation. So what this says is, don't go to such ridiculous numbers like 100 weeks. This model is not good enough. Even for 10 weeks, it may not be appropriate. So no question of 100 weeks. So the first thing to remember for a user of regression equation, don't extrapolate too far. If you have data for 6 weeks, then maybe 7 or 8, a couple. Okay. And now these are data from WHO's website. And what is on the x-axis? Year. And what is on the y-axis? Total number of adverse reports recorded in that website. So these blue points are the cumulative values. And then I fit the model. And look at this model fitted. Incidentally, Excel will do it in 1 second. A value is 417.8 and E raised to 0.1731 times X. So I'm interested in this 0.1731. And the R square of this model is 0.84. That's a good R square. Once again, blue are the actual data points and red dots are the fitted ones. Okay. This you can do for every drug. There were several drugs. And then compare the estimates of B. And my next table, look at this. Estimated growth rates and R square values for 6 alternatives to ranitidine. So famotidine, its R square value is 65%. I want a reasonably high R square value. Otherwise, that model does not fit and it doesn't work for that drug. But most of the values are high. Some are much higher. In case of calcium carbonate, it is 94%. In case of rabeprazole, it is 84%. These are very high values. In case of pantoprazole, it is 93%. These are quite high values. Okay. Now I have ranked by the value of beta. Okay. And I claim that smaller the beta, safer the drug. All right. So by that reckoning, famotidine is the safest, next is rabeprazole, etc., etc. So if you ask me, I would say choose ones with low value of beta, but high value of R square. And therefore, I would much rather go here. So in my opinion, if you accept my approach, rabeprazole is the safest alternative to ranitidine. And what is the shape that you expect? If on the x-axis I have year and y-axis I have total number of adverse reports about that drug with the WHO up to that year, what is the shape? Well, depends on what happens. If it is a banned drug, after banning, presumably, nobody uses it. And therefore, there are no new adverse reports. So initially the total will keep on increasing and after banning it will kind of become horizontal. This is the expectation. So we said, the count should keep rising until the year of banning and flat afterwards. This is the expectation. Because if nobody is using, there is no adverse report. Then we started checking what it is like for different drugs. How does the actual data behave? Okay. So example 1, this is the drug Cetron by Prometheus Laboratories, and this is for diarrhea, anti-diarrheal. And let us see what it looks like. It was withdrawn in 2000. Okay. So here is the picture. On x-axis, you have the year, and on y-axis, total number of adverse reports. And see, it is after 2000 only, not the earlier ones. So one expects that it should decline. When it is banned, people will know about it later on. Until then, they will keep buying. If they have already bought, they will keep using, and therefore there will be adverse effects. So we expect that there will be some adverse reports even after banning, but slowly it will stabilize. So you can see this. At 2000, I started with 0. I forget the earlier ones. You still keep getting reports. These are yearly, and this is the total. And the total stabilizes. This is the picture that I expect for banned and withdrawn drugs. Unfortunately, so what happens is if you see primary
data will be analyzed. If safety data is available, the subject will be analyzed for safety analysis and for efficacy or immunogenicity, whatever is of interest final. If data is available, the subject, but not complete data, then subject will be analyzed in the intention to treat if pre and post some comparison, or at least would be added in the descriptive summary stats. But intention to treat analysis is that if data is available, need to analyze. And from per protocol, the data will be out.
Right.
Because
So
it's of no meaning.
Yeah, by and large, even if the patient does not complete the trial, any adverse event he experiences must be taken into account. But whether information should be used in efficacy is a question.
Yeah, thank you, sir. We had a great time and we learned a lot. Everyone, even
Wow.
I learned a lot. Your examples were great.
Thank you.
Yeah, as Monisha said that you made the dry subject really interesting. That's what, because without examples, no one will understand otherwise so easily the statistics.